So Eevee has this one move called continuous steps. If you don't know, in the card game Pokemon, you play your Pokemon and they fight the enemy's Pokemon, and they have these little attacks. Eevee has one called continuous steps, and it says it doesn't tell you how much damage it does. It says 30 times damage. So it does a variable amount of damage. Sometimes it does more, sometimes it does less. And the instructions say, flip a coin until you get tails. This attack does 30 damage for each heads. For each heads you got, it does 30 damage. You flip until you got a tails. The attack does 30 damage for each heads. That is a random variable. This is the kind of thing we're doing in the course. Even though it's in a kid's game, this thing is so fundamental, it appears in Pokemon. And the question we have for you to start out with is some basic questions about Eevee. Who's that Pokemon? It's Eevee. Answer these questions about Eevee's continuous steps attack. And I have 3 quick questions. One is, what is the maximum amount of damage Eevee can do? That is very useful to know, because in Pokemon, if you deal enough damage, you can knock out your enemy's Pokemon. That's very good. That's important to know. The most likely amount of damage, that one is harder, also important to know. And last but not least, we've mentioned this a couple times, there's continuous and discrete random variables. We haven't told you the actual definition yet, so we're kind of going on vibes here. Do you think Eevee's attack, let me put Eevee back up just for 1 second so we can see it. Do we think Eevee's attack, is that a continuous random variable or a discrete random variable? We've talked about it a few times. I won't say any more hints right now. You do you and tell me what you think it is. All right. Questions or comments about the questions or comments? Who's as excited for Pokemon as I am? Almost nobody. That seems accurate. Okay, let's. I'll give you guys a couple minutes, and we will take up these warm-up questions that are going to lead us into our next topic. All right, let's take a look. I heard some hairy discussions about how much damage Eevee will do, which very much reminds me of myself on the playground many years ago with the Pokemon cards. Let's see what people said, and let me put this up. So we all remember what Eevee does now. 30 damage per tails. No, 30 damage per heads, and you flip a coin until you get tails. Let's put this back over here so people can see easily. What did people say? The maximum amount of damage that Eevee can do is... All right. 27 people wrote infinity. 12 people wrote does not exist. Of course, in this course, we've been using does not exist for I have no idea. But in this case, does not exist is a potentially correct answer. So what does infinity mean? You might have heard the famous saying, infinity is not a number. I think the most correct answer is does not exist. I think does not exist is the right answer for this one. The reason it does not exist is because no matter what number you say, Eevee can do more damage than that. All right? So somebody comes to you and says, I think Eevee can do 150 damage. And then I'll say, well, yeah, but they could also do 180 damage. And then someone comes to you and says, I think Eevee could do 3 million damage. And you say, yeah, but it could do 3,030,030 damage. So the idea of the maximum is the number that is the biggest possible number that it could do. Of all the numbers that Eevee could do, the maximum is the biggest one. And there is no biggest one. There is no biggest one. It does not exist because no matter what number you say, there's always a number that is bigger than it. Some people think that this is infinity. And indeed, infinity is all about this idea. But I wouldn't say the maximum equals infinity. I would say there is no maximum. And I would say there is no maximum because the set is unboundedly large. There is something called a supremum. A supremum, if you want a $1 million word. The supremum, and that one is infinity. So the maximum of, let's say, of Eevee's damages, Eevee's possible damage. I would say this does not exist. If you've been taking calculus, you will know that a limit at infinity is a special type of does not exist. So this is the special type of does not exist, where it is some kind of infinite, but I think the most accurate answer is does not exist. And I'll say one more thing. There's something called a supremum that you will learn if you take real analysis class. And the supremum of Eevee's damage, this one absolutely is infinity. Possible damage. And a supremum is something like a maximum, but it fixes situations where it does not exist. in a very technical, nice way. Supremum is a nice Latin word. I believe it's the Latin word for maximum, so it's a little confusing. But that's the answer to the first one. Would you say it doesn't exist, Professor Humphrey, or would you say it's infinity? Or are they the same to you?
I would probably say tends to infinity.
Tends to infinity. So the reason I wouldn't say tends to infinity is because it's just, there's no order. There's nothing moving, right? It's just like we have a collection of numbers. If we were going to say, as the number of coins you get that are heads in a row increases, the amount of damage tends to infinity. I would say that. But I would want, before I say tends to infinity, I would want some kind of like motion process somewhere, which you can put in. As the number of coins increases, the amount of damage increases to infinity. That is a valid statement, I think. Yeah, so you just gotta be careful. Basically, infinity is a special word, and you gotta be careful with infinity as you're learning if you're taking calculus. Any questions or comments about that first one? Okay, I think most people had the right idea for that one. The answer is certainly not 30, because if you just get two heads in a row, you'll deal 60 damage. Okay. Here's another one. Okay, this is maybe an easier one we should do next. What type, either continuous or discrete, is this random variable? Let's see what people said for this one. It's almost perfectly split. 22 discrete, 23 continuous. Just a very small extra little boost for continuous. And I think the reason you guys voted for continuous more often than not is because the name of this attack is continuous steps. Continuous steps. All right? So if you believe the people at Pokemon HQ, then you would think it's continuous. The answer is discrete. It's discrete. If you picked continuous, you're wrong. This is a very poorly named Pokemon card. I do not know why they named it continuous. Let me write down a word on continuous versus discrete. So here is one way I like to think about it. Discrete can write out the values in, and I'll say possibly infinite list. So you can write out the values. What are the values Eevee can take? 0, 30, 60, 90, and then the infamous ... right? So that is why it's discrete. You can list them out. It's either 0 or 30 or 60. It's these predefined things, and it kind of jumps from one to the other. Discrete is this idea of sort of an indivisible piece, right? The 30 is either 30 or it's not 30. Whereas continuous is slippery. It's kind of, let me think of it this way. It's like smudged across continuous. And again, I'm using continuous to define continuous. We're going to have a better definition later. Set of numbers. And an example would be something like the interval. So if you know this closed bracket notation, the interval 0, 1, if a random variable could take on all the possible values in the closed interval 0, 1, you can't list them out. You can't say 0, 0.1, 0.2, 0.3, because then you've missed the 0.01s. And you can't just say 0.01, 0.02, and so on, because then you've missed the 0.0001s. So no matter how hard you try to list out these numbers, you won't be able to do it. We're going to see that later. And this thing has the property that is uncountably large. That is the real key defining thing. And uncountably large means basically it cannot be put in a list. Cannot be listed. We're going to see maybe this later. But this one is discrete despite the name, which is why it's such a great example. Because if you ever need to remember, just remember that the Pokemon card, they named it wrong. It should have been discrete steps, not continuous steps. So these two ideas of going off to infinity and being discrete or continuous are kind of separate issues. You can still go off to infinity even if you're discrete. Questions or comments about discrete versus continuous? Yeah. The binomial is another version of a discrete. The binomial, that was an easy one where the possible outcomes were 0, 1, 2, ... up to n. So not only were they Listable, it was a finite list. There were only n plus 1 ways it could come out. Remember we had that class question, is it 10 or is it 11? Either way, it's definitely not some huge infinity of numbers that you can't list out. You can list out the numbers, and therefore it's discrete. Yeah. So that's what discrete means, listable, outable. So for the binomial, there's n plus 1. Not only is it listable, it's even finite. So there you go. Okay. Other questions? Okay, let's go back to the probability question, which is, again, this is the kind of thing that using the probability tools that we did before, you could figure out. And in particular, you can draw a big probability tree to figure out this most likely amount of damage. Let's see what people said. 23 people said 30. 23 people said 30. 30 seems right, and there is something special about 30. I could change this to the blank amount of damage Eevee does, and the correct answer would be 30. But for the question, the most likely amount of damage that Eevee does, the answer is not 30. The answer is 0. 0. How many people got it? Only 9% of people. The most likely amount of damage that Eevee does, it is 0. It will turn out that the average amount of damage Eevee does is 30. So this is where we are going. Let's write these down. So let's recall in our notes. Eevee, what do they do? I keep spelling their name wrong. Eevee, flip coins until a heads. What is it? Or flip until you get tails. Which one was it? Flip until you get tails. Until tails. 30 damage per heads flipped. Okay, and here are two facts. Fact number 1 is the most likely outcome. Most likely outcome is 0. And fact number 2, this is kind of a bonus fact. We're not going to get to this this class. We'll get to it in a few classes. The average outcome is 30. So that might be why people were saying 30, is they might have had in their head, okay, I'm flipping coins, either heads or tails. There's 2 possible outcomes, so half the time. And then they were thinking of averages, and if you got averages, it is indeed 30. We're going to do this later. The one we're going to do now is this one, the most likely outcome. Is there a problem, Professor Humphrey? Do you think maybe I made a horrible mistake? You don't like the word average. You think average is not a good word. You think we should say mean?
It's problematic here.
Mean. Okay. But this makes it seem like the outcome is unkind. That's not what I mean.
Is the mean 30?
I wouldn't write either of these. I would write the expected value, and then nobody can argue with you because it's so precise.
So,
but maybe you're saying it's something other than 30. I thought it was 30. 1 over p minus 1. No, come on, it's 30.
That's 1 over p.
Yeah, but no, you got a minus 1.
We have to decide.
You have to subtract 1. It's 1 over p minus 1. It's not 1 over p. Okay, well, there's a debate amongst the people with PhDs. or is it 60? We don't know.
Well,
Should we attach our names to the predictions, Gary? Do you want to?
I will attach my name.
All right. Well, this is exciting. This is Prof. Humphrey thinks that it's 60, and Prof. Nika thinks that it's 30. Who's right? We're going to find out next time on Pokemon. No, we'll find out at some point in the future. I really think it's 30. 60 is crazy. That card would be way too good. That's the real thing. If it dealt 60 damage on average, that would be a killer. All right. That's the real reason I know it's 30. Okay.
Oh, you're saying you're not going till you get.
You got to read the card. Oh, this is a classic mistake of Pokemon cards, is misreading the cards, and I think that's the mistake. Let's see. Yeah. Okay. So are you retracting your?
I'm going to retract.
Okay. All right. Okay. We're good.
Yeah.
Amazing. Okay.
Yeah.
This is very exciting. Yes, there is. It turns out later on there is a formula that the formula goes 1 over p. But there's another formula called 1 over p minus 1, and sometimes it's 1 and sometimes it's the other. We're going to talk about this later. We're kind of getting ahead of ourselves.
Just a second, then. Just a second. The most likely amount of damage.
Yes.
Is
Yeah. We're going to do it right now. Let's do the most likely damage. So we're going to do a little tree. How much damage did Eevee do? this is a tree. And I think this is the thing to emphasize is all the stuff we did before the midterm. That is how we solve all the problems after the midterm too. It's just we like bundle up the things. How much damage did Eevee do? And we can draw a probability tree. The probability tree is going to lead us to different outcomes. We know how to do probability trees and find different outcomes. A random variable is just bundling up all the outcomes and saying, look, there's the outcome x equals 1, there's the outcome x equals 2, there's the outcome x equals 3, and so on, and thinking of them all together at once. That's what a random variable is. And it comes with some extra things like the average value and so on. But at the end of the day, you do it with the probability tree. So let's do the tree. How much damage did Eevee do? Well, we flip the coin, and either we do heads or we do tails. And Eevee says, let's read the card one more time to make sure we're not doing it wrong. Flip a coin until you get tails. The attack does 30 damage for every heads you got. So you can either get tails or heads. And if you get a tails on that very first flip, you go to flip the thing, and you get tails. Let's show the card so everyone can agree with my interpretation of the rules. Is anyone here certified as a Pokemon rules judge? Nobody. OK, we'll have to do our best. The flip a coin until you get tails. The attack does 30 damage for each heads. So if you got a tails on your very first flip, by my math, you have 0 heads. And therefore, it does 0 damage. 0 damage. So it does 0 damage. So the amount of damage equals 0. Let's put that in red because it's so important. 0, big fat goose egg. So half the time, 50%, the damage is 0 going down that branch. The other half of the time, you got a heads, and you get to flip again. And now, and let's write the probability underneath in purple. Purple for probability. Probability is 50% to get 0. What about if you flipped a heads? Well, then good for you, you get to flip again. And you can either get a tails or a heads. And they are 50% each again. And this time, if you got a tails on the second flip, you've got at least 1 heads. And so the amount of damage is 30. Damage equals 30. And so the probability is, what is the probability? You've got to do the multiplication rule. 50% times 50%, 50% times 50% for each layer, also known as 1/4. So the probability is a quarter, or we could say 25%, to get 30 damage. If you've gotten really lucky, you've gotten 2 heads in a row, then it splits off once again. And so it could go like this, tails, heads. And again, these are both 50%, 50%. In the situation where you got heads, heads, then tails, then now you have done 60 damage. And this probability is the multiplication of 3 layers. The first layer, the second layer, the third layer, a half times a half times a half, also known as 1/8. Maybe you can spot the pattern. The probabilities go a half, a quarter, an eighth, and they just keep going forever. This is, again, the return of the infamous ... So which outcome is the most likely? Well, 0 is the most likely. That happens half the time. And everything else all combined together is another half the time. But every individual outcome over here is at most a quarter. So it's a half, a quarter, an eighth. Goes down forever. The most likely is the first one, which is 0. So therefore, the probability that the damage equals 0 equals 0. That's 50%. And that is the most likely. Let's put this back in purple. Is the most likely outcome. It's the outcome that has the highest probability. OK. So this is very interesting to get your head around. I think this is one of the cool things about infinity, is because this goes on forever, even though 0 is the most likely outcome, on average, you still do quite a bit more than 0 damage. You actually do this much damage on average. And that's because all of these like infinitely many outcomes over here are pulling up the average. So even though 0 is most likely, the average is big enough that this is still a fun Pokemon card. We're going to see some stuff about that later. But this stuff can be kind of counterintuitive. Starting to flirt with infinity over here and work out some hard stuff like this. Got the ... tree that goes on forever. You have to imagine it in your head. But this is a very fun kind of random variable to work with. Any questions or comments about this one? So this random variable has a name. What is it called? What is this random variable called? Just like the binomial, it has a very famous name. Random variable called. And it is named after this sequence. So there's a name for this sequence, the sequence 1/2, 1/4, 1/8, 1/16, ... This sequence has a name. you might have seen the name of the sequence in high school. Does anyone know the name of the sequence? Okay, then you will find out today, because the name of the sequence is also the name of the random variable. They are both called geometric. Geometric. This is a geometric sequence. That was where the probabilities. And this is a geometric random variable. We have a nice little slide here with telling you more about a geometric random variable. Did it pop up? Okay, very nice.
Okay,
There it is.
we're ready to roll. Geometric. Card back.
Oh yes, we can't forget Eevee.
Geometric distribution, notes, very blank. I would, as I did in the binomial, often start with the probability mass function, in other words, the equation that's going to give us the probabilities for a geometric distribution. But there are a couple little tricks with the geometric distribution. But first, what we're going to do is start off by deriving it. Rather than just look at an equation, we're going to go back and then we'll fill that equation in. So let's consider the derivation. And I'm going to start with a real simple example. Very similar to the, well, actually the Pokemon one has got an extra little complexity to it. But I'm going to start with, let's give me a dot camera. That's what I need is a dot camera. Here I go. Okay.
Gary, you should know it's very zoomed in on your hand right now.
Oh, very
it was zoomed in on the Pokemon card.
That's so frightening.
Yes. Okay.
Yeah. Let's get that down. So just consider rolling a fair die until a 6 is obtained, okay? So what I want to do is define x, number of rolls required to get the first 6.
Hold on, I have a very important rules question.
You do have an important
in
rule.
Eevee.
That's not the definition.
In Eevee,
yes.
it said, what did it say? It said the number of heads, right? It does damage based on the number of heads. Is that the same as what you wrote over here? Like if we were making a Pokemon.
Not exactly.
Oh, haha. So this is the number of rolls required, and that includes, I guess, the last roll.
Oh, just a sec.
I zoomed in a little bit too much. Okay.
Okay, that's what you did.
So this is very slightly different than the Eevee because this one, you're guaranteed to have at least one roll. But in the
I'm
Eevee,
guaranteed to have a roll.
In the Eevee, you could have dealt 0 damage.
I could have dealt
And
0 damage.
So actually, there's 2 flavors of geometric distributions. They either start at 0 or they start at 1. The one you're doing is the one where they start at 1.
Yes.
Okay, very good.
Then we will
Good
do the one with
clarification.
0. Yep. Okay. So this case, number of rolls required to get the first 6. I could have defined my random variable differently. I'll do that a little bit later on the slide. I might have defined it as the number of rolls before I get my first 6. Okay. We'll come back to that one, but let's just probably this is the most common way the geometric distribution is defined in statistics. Not always, though.
This is a classic problem even in programming. Do you start at 1? Is the first number 1, or do you start at 0?
Yeah.
Everyone always debates. There is no right answer. Sometimes you want to start at 1. Sometimes you want to start at 0.
Yeah.
Eevee starts at 0. This problem starts at 1.
Right. So we can define x equals number of rolls required to get the first 6. And, you know, if we did this, you say, well, the probability x equals 1, we got to roll it once before we get our first 6. I'll call that p of 1. That's just going to be 1 out of 6. So then let's continue thinking about this. What's the probability x equals 2? What's the probability I'm going to have to roll it twice to get my first 6? Well, in order to get my first 6, the very first time, I have to have failed to get a 6. So we can think of this as, you know, 5/6 chance that I didn't get a 6 and a 1 out of 6 chance that I did get a 6. So I need a failure, and then I have to get a success. Okay, well, what about the probability x equals 3? For the probability x equals 3, I'm going to have 2 failures in a row. And so to get 2 failures, first of all, a non-6 and then another non-6, that's going to be 5/6 times 5/6 is 5/6 squared, times then the probability of actually getting a 6. Okay, so you can think about how this is moving up there. Now, we could also consider, what if the die was not fair? Such that the probability of rolling a 6 is not necessarily 1/6. So we'll just call it is just a general p. Okay, and
Wait. You already have a p. You have p of 1 and p of 2. It's the same p, right?
it's no, they're different p's.
Oh, wait, and then there's a p over here.
Yeah, I know that we got to get used to them. You know, they even get used to names like Peter and Paul. You know, these are different p's.
So that's a different p. Okay.
This is a functional p.
Yes, p with brackets is the function. P with no brackets is the number.
And
Sorry that
we
life
like
is
our
like
p's.
that.
We like our p's.
Well, we don't like them, but this is the
Yeah.
universe we're stuck in.
Yeah. So probably rolling a 6 is p. Therefore, the probability of rolling something other than a 6 is q equals 1 minus p. Okay, so we're just going to think of that. And so if we were to redo these, let me just consider taking that one off for the moment. Redoing the above probabilities. I mean, we might say probability x equals 1. Call it p of 1. That's going to be, well, it's not 1 out of 6 necessarily. It was just going to be, call it some general p. And the probability of a the probability of a 6 could still be 1/6 because it just said the die is not fair, so that means that all the other things aren't necessarily equal to 1/6. The probability of a 6 could still be 1/6. But anyhow, there's a general p there, and then the probability x equals 2. P of 2 is going to be, okay, in order to get my first success, my first 6 on my second trial, first of all, I have to have failed to get a 6 on my first trial. That occurs with probability q, and then I need to get my my success, my 6, with probability P, and we do the probability X equals 3 is going to be P of 3, and that's going to be Q squared times P, because I have to get 2 non-6s first, 2 failures, and then I get my success of a P. And I think what we're seeing is that if I was to say that X takes on any particular value, which we'll call little x, let's just think about what that requires. In order to get to the X trial, I first of all have to have X minus 1 failures. So this is going to be Q to the X minus 1 times P. So what we've actually done is we have actually derived the geometric distribution. Where X equals number of trials, and this is important. Professor Nika is totally on top of this thing here.
I've
X
been
equals
burned
the
in
number
Pokemon
of trials required to get the first success P equals the probability of a success on any trial. And trials are independent. So we've basically got it summarized there. We could summarize one little extra bit in a nice clean form. We've got P of X equals Q to the X minus 1 times P. And, well, we'll kind of write that out in a little bit. Let's just look at a couple more slides first. Let's go back to slides.
Wait.
Slides.
I drew a picture I want to show everybody.
You want to show your picture.
I drew exactly what we did, but I added some pretty colors, and I put it in a tree. You see?
You do.
So instead of just saying we got two failures and a success, now we go along the tree. Fail, fail, success. So the Q's are the going down this way. The P's are when you exit, and so you always have one P for each one, and the number of Q's you have is the number of layers before your thing. The total number of things you multiply together is equal to which layer you're in. So probability X equals 2 is a Q times a P, 1 Q, 1 P. Probability X equals 3 is a 2 Q's and a P, and then it's color-coded. And I was about to fill in what's probability X equals X, but you can do that yourself.
How far does that tree go down?
Well, the dot, 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 see? Dot, dot, dot. The heavy lifting. This is how we, this is the version of then the magic happens.
This is very dangerous. Could go right through the floor.
Yeah. Well, you know, that's where the tree starts.
That's a very nice tree.
Thank you.
I like
Thank
your
you.
tree.
I worked hard on the colors.
Okay.
Yeah.
So I want to just zip through a couple slides here. Again, these are up there in the pre-post there too. Don't worry about writing them down. So what we've done is we have actually derived that distribution. Well, here's what I would like you to, we're going to write that one out in a moment when we define a couple things. And so here's a key thing, is that the conditions for a binomial distribution, a couple of those conditions are exactly the same for the geometric distribution. The trials have to be independent of one another, okay? So this can be done in a sampling with replacement situation. And there's a constant probability of success on each trial, okay? Again, that's another necessary condition here. Now, what is different is the way the random variable gets defined. And instead of conducting a fixed number of trials and counting how many successes we have, what we're going to do is keep conducting trials until we get our first success and count how far it takes us to get to that first success. So the way I've defined the random variable there, x can take on, in order to get our first 6, for example, we had to roll the die once, okay? We had to have a trial before we could get a success. So we're going to have a little bit more to say about that random variable in a moment. But the point is we're going to have to roll it at least once. Maybe we're going to have to roll it twice. Maybe we're going to have to roll it 3 times. But we can't ever state how many times we might have to roll it. The random variable x there, the number of trials that it takes you to roll until you get that first success, that is a discrete random variable. It's also a discrete random variable that takes on a countably infinite number of values, okay? And so we don't know what that value might be that it's going to take us to get to. Whenever we do get that first success, we can count to that number of trials it took. We have a single parameter in this distribution, which is p, and that is the probability of the success on each trial. The q is just automatically determined. The probability of a failure is 1 minus p. And as we will get into the mean or expected value, we will see that it is 1 over p. But let's kind of just intuitively think about that. Consider if we had our die was a fair die. You know, we know there's 6 different sides to it. And you kind of think of, okay, on average, how many times are you going to have to roll that die to get your first 6? Well, sometimes you're going to roll the other numbers. And there's a probability you get a 6 on that first trial. But it kind of makes sense that on average you're going to have to roll the die 6 times to get 1 of each number. Okay? We'll have a more formal derivation of that.
Another way you can think about it is if the dice were rigged so that like you can't have multiple things coming up. Like if once you've rolled a 3, you can't roll another 3, then a 6 would come up every 6 numbers. Like the numbers would get used up. First you use up one of the numbers, then another one, and then another one, and eventually you get the 6, and then 6 ones later you'd have another 6. And so sort of if there was no randomness in the world and the dice was just spitting out the numbers kind of in order, it would be 1 out of every 6. And that's what it is even with randomness.
It is with randomness.
So the averages are really nice because they kind of make random things seem less random. That's fun.
Mm-hmm.
Mean. I don't know how I feel about mean because there's different types of means. Do you ever say like the geometric mean or the
harmonic mean, geometric mean?
We mean the, I guess,
arithmetic mean.
Well, no, but not quite because it's. That's why I don't like mean. There's too many means. Okay.
Too many means.
Some people say other letters, other words.
Okay. So let me just, we went to that point. We got everything defined there. And I just wanted to summarize. Let's see, where's our time here? Okay, let's kind of just keep an eye on the time. And go back to, the dot camera. You're already on top of me on that one there. Okay, so. So we want to actually just write this probability mass function out correctly, or sort of leave it very well defined. Q to the x minus 1 times p, x equals 1, 2, 3, and so on. And then we say 0 otherwise, because we can't, for example, roll our die 1.5 times or 3.2 times, something like that. And the way this is defined, for example, the probability x equals 0 is going to be 0 because we have to roll it once before we get that first success. Now, this is kind of a, oops, well, it's also something you can't see, which is an issue. That's what I want. This is kind of a cool thing, is this little statement. It looks kind of weird, but if you kind of think it out, it kind of makes sense. And it says, what's the probability it's going to take you more than a certain number of trials to get your first success? Well, if, for example, we were to say, what's the probability it's going to take you more than 4 trials to get your first 6? Well, in order for it to take more than 4 trials, it means that I failed for the first 4 trials. And the probability of a failing for those first 4 trials, or any specific number of trials, is just going to be all failures in a row for A. And so this allows us to get the probability, the cumulative probability distribution. Probability x is less than or equal to A is just going to be 1 minus that. In other words, I will get my first success within a fixed number of trials if I didn't fail for all those trials. Okay? So that's kind of like weird in a way, and it's kind of like you kind of got to think it through a little bit.
Yeah,
a little bit.
I drew another picture.
You drew another picture.
Look, we're saying instead of doing the individual outcomes on the tree, you can group a whole bunch of them together. And here I've grouped everything past x equals 1 and x equals 3. I grouped it all together. That's the event that x is greater than 2. If it's not 1 or 2, it's got to be greater than 2. And all of that together is probably x is greater than 2. And how do you get there? Well, you got to do a q and a q. So it's q squared. There should be a q squared there. That's exactly what was just said to you without the beautiful picture that I drew.
Yeah.
All right.
That is a beautiful picture, too.
Thank you very much.
Did you ever consider becoming an artist?
I did. They didn't let me in art school. They said, go do a math PhD.
What a... Well, it's not a waste.
Well,
Mathematics itself is an art.
Yes. Okay.
Okay. Okay, so last point on this one for today, I guess. Did you want to do a mathematize for next day?
Let's just do a hand vote.
Okay.
Quick hand vote.
Okay, so I put a caution here. Some software programs use an alternative definition for x, such as defining x as the number of failures prior to obtaining the first success. Okay? And in fact, that is the definition that worked best for our Eevee example. And I will also mention that R uses that definition of x. So why did I use the definition I started with? That is the one that you will most frequently see in statistics books, mathematical statistics books, but we have to be aware that there are these two very similar definitions. You know, the difference between them is just a difference of 1. You just got to watch for them as to how they're defined, okay? So that's all for today.
Yeah, so you have a homework. It is due on Monday, so if you want to rest a little today, you can do it on Monday. There will be another one posted, hopefully today, for next Friday. So keep an eye out for that. That one will be on the binomial random variable. But otherwise, have a good weekend and enjoy your Pokemon card playing.